Hello children, this is Edison. In this video, I am going to teach the chapter Matrices. The topics will be covered in this video: the definition of the matrix, order of the matrix, types of matrix, operations on matrix, and the inverse of a matrix. The definition of a matrix. A matrix is a rectangular arrangement of the elements. It will be arranged as a horizontal and a vertical. For example, we can take the matrix 1, 2, 3, 4, 5, 6, 7, 8 like this. So the numbers I have taken 1 to 8, it is arranged like this. Even I can arrange these numbers 1, 2, 3, 4, 5, 6, 7, 8 also. Even I can arrange the same numbers like this, children. It is 1, 2, 3, 4, 5, 6, 7, 8. Like this also I can do the arrangement. Okay, children. Yes. So that means here, what do you observe from this means, children, here we can see the horizontal lines. The horizontal. Two horizontal I see. This horizontal arrangement are called row. So it is R1, this is row 2. Then this actually we are having one vertical, second vertical, third, and four verticals we are having. The vertical arrangements are called column. So it is C1, C2, C3, here C4. There are two rows and four columns. Two rows and four columns. Okay, here horizontal, how many? 1, 2, 3, 4. So row 1, row 2, row 3, row 4. Okay, there are two vertical columns only. It is vertical arrangement C1 and C2. So here we can say 4 rows and 2 columns. Okay, children. Similarly, for this we can say that 1 row, 8 columns. Okay, children. Yeah. So this is how we do the matrix arrangement. Okay, children. Row and a column. Row is horizontal. Column is vertical. Okay, children. Now we see the order of the matrix. That means a matrix has what? M rows and n columns. Means we can say the order of matrix A is nothing but M cross N. Okay, we can call this as M cross N, or we can read it as M by N matrix. Okay, children, like this also we can do. So what about this? The matrix what I wrote over here, it is 2 by 4. This actually 4 by 2 matrix. This is actually what? 1 by 8. We may be having the question, sir, why don't you write the column first? We are having the uniform idea to represent the order of the matrix is first number of rows first, then second number of columns. Okay, children, that is why we use that m by n, so m rows and n columns. Okay, children, and we can represent any matrix like this. It is Aij, okay, or m by n. Children, it means I represent ith row, J represents jth column. Okay, that's what. So that means ith row, jth column. For example, if I take the matrix A as Aij, okay, it is 2 by 2 matrix. That means it has 2 rows, 2 columns. Okay, so that means, children, the matrix will be written as what? A11, A12, A21, A22. So this means, what is A11? A11 means first row, first column. Okay, if I say that A21 means it is second row, first column. You understand, children? We can say all. like this. So this is actually what? Second row, second column. This is actually what? First row, second column. Okay, children, of any matrix we can represent in this form. So if they mention that A32, what does it mean? Third row, second column. Okay, children. Yeah. So this is how. So if example Aij, if they are giving us I plus j by 2, then can you say what is A21? It is 2 plus 1 by 2, which is 3 by 2. Like this, children. So they will ask you to represent the matrix by giving Aij equal to Ai plus j by 2. Then find the matrix of order 3 by 2 or 2 by 3. Like that and all they can ask. Okay, children? Yeah, nice. Children, now types of matrices. In types of matrices, we have the first category, it is a row matrix. Children, row matrix means it has only one row. Okay, it is a matrix has only one row. N columns is nothing but a row matrix. Okay, yeah. So this can be represented, children, if generally if take A equal to Aij, okay, m by n. Okay, the order is m by n means, children, we can say that m is equal to 1. If the matrix of order m by n, if m is 1, that means if the number of rows is 1, then we can say it is row matrix. Okay, then for column matrix, children, it is just m by 1. That means what? There will be only one column. So this means only one column. If a matrix has only one column, m number of rows, any number of rows, then we can say it is a column matrix. Then here the square matrix. Square, if a matrix has equal number of rows and columns, that means I take m and n, no. So here if m by n, this implies m is equal to n. The matrix has same number of rows and columns means we can say square matrix. Okay, children, when we talk about the square matrix, we can say that it is 2 by 2 matrix, 3 by 3 matrix. Like this we can say. For example, 1, 2, 3, 4. See that it is 2 by 2 matrix. Then for 3 by 3, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, this is 3 by 3 matrix. So when we talk about the square matrix, children, so order of, okay, order of square matrix. We have to say in only one number. So that means if it is 3 by 3, 3 by 3 means we can say that order as what? 3 itself. For this also we can say that order is 2 only. But for other rectangular matrix and all, we have to say 2 by 3, 3 by 4, 4 by 5, like that. Okay, children? Yes. Now, this is what is square matrix. Then we come to the diagonal matrix, children. So diagonal matrix means, children, first of all, we need to know what is a diagonal element. What is diagonal? Children, diagonal is nothing but, children, it happens only in the square matrix. You just see, I'll just show over here, children, this. Okay, you can see this is called a leading diagonal. You know this position is A11. This position is A22. This position is A33. Okay, children. Now see that I and J both are equal. Here you can see I and J both are equal. Here also I and J both are equal. So, children, the diagonal elements, leading diagonal elements, which are Aij, okay, when I is equal to J. Okay, children. So this is called a leading diagonal. You may be thinking, sir, diagonal 3, 5, 7 also no, sir. Like that we may be thinking, but that should not be taken because here I is not equal to J. You know what about this one? It is 1, 3. This is 2, 2, okay. But here what it is? It is 3, 1. They are not same. Children, do you understand? When I equal to j, all aij called the leading diagonal element. Children, when we now we come to the diagonal matrix. In a diagonal matrix, so all the leading diagonal elements will be some non-zero number. So other than the leading diagonal, all the elements are 0. We can represent like this: aij is equal to 0 when I not equal to j. Okay, children, aij is 0 when I not equal to j. So for example, we can say that 2, 0, 0, okay, yes, 0, 5, 0, 0, 0, 7. See here, children, now the leading diagonal elements only non-zero, all the others are 0. So other than the leading diagonal elements, if you find the numbers are all 0, we can say it is a diagonal matrix. Okay, children, yeah. Then next, and also one more thing we should remember here, m is equal to n, same number of rows. That means it is happening in the square matrix only. Okay, children. Yeah. Now see the next, scalar matrix. Children, scalar matrix is nothing but all the leading diagonal elements are same. Okay. In a diagonal matrix, if you find all the leading diagonal elements are same, means we can say it is a scalar matrix. For this, we can say it is, this is 2, this is 2. See that 2, 2, 2. Okay, so this means we can say this as aij is equal to, then it is some constant k when I equal to j, and 0 when I not equal to j. You understand, children? Scalar matrix means aij is equal to k when I equal to j. Aij is 0 when I not equal to j. You can see this as the example. Okay, now we come to the identity matrix or unit matrix. Children, the scalar matrix we said from the diagonal only, because diagonal elements only. We talk about the diagonal elements only. Same thing, children. If all these diagonal elements are equal to 1, children, it is identity. See, so I'll just write aij is equal to 1 when I is equal to j. What does it mean? The leading diagonal elements all are equal to 1 and 0 when I not equal to j. That means the elements which are other than leading diagonal elements all are 0. Okay, children? So that is what. Now, next, zero matrix or null matrix. Children, it is very simple. All the elements involving in the matrix are all 0, is nothing but zero matrix. That means we can say aij is equal to 0 for all I and j. Okay, you give any value for I, any type of matrix you can take. If all the elements of 0, we can say this is zero matrix. Okay, children. So for example, we can say 0, 0, 0, 0, 0. This is also zero matrix only, children. Null matrix. Okay. Yeah. Now transpose of a matrix, children. Transpose of a matrix means interchange of the rows and columns. Okay, interchange of rows and columns. If I take that matrix A is 1, 2, 3, 4, 5, 6. The transpose of this is nothing but the row 1, 2, no, it becomes column. The row 3, 4 becomes column. The row 5, 6 becomes column. Okay, children, now you can see that it's actually 3 rows, 2 columns. Okay, then this becomes 2 rows, 3 columns. You understand, children? 3 rows, 2 columns, change it as 2 rows, 3 columns. We can represent this as A transpose, or we can say that as A dash. Okay, children, that's what. So interchange of rows and columns called the transpose of a matrix. Okay, children, so it is A dash or A transpose is equal to, children, you know that Aij, okay, of m by n, it is transposed means it become Aij, okay. it is n by m. The order is changing. Can you understand that? Order is changing. Okay, children? Yes. Now, triangular matrix. In the triangular matrix, we have the two category. One is lower triangular matrix and the upper triangular matrix. Okay, children, the elements which are above the leading diagonal all are zero means we can say it is lower triangular matrix. That means I can say that 1, 0, 0, okay, 2, 5, 0, 3, 6, 7. Now, when you look at this, children, above the leading, this is the leading diagonal. Okay, above this leading diagonal, we can see these elements are 0. Okay, this is called a lower triangular matrix. We can represent this in another way. It is Aij is equal to 0 when I less than j. Why it is? Here this number shows that the position 1, first row, second 1, 2. This says that A 1, 3. This shows that A 2, 3. You can see that 1 less than 2, 1 less than 3, 2 less than 3. Is that clear, children? Yeah. Next, upper triangular matrix. This means below the diagonal elements. Below the diagonal elements, all the elements are 0 means we can say it is a upper triangular matrix. See, children, 1, 2, 3, 0, 4, 5, 0, 0, 6. You can see that it is 6, children. Okay. So now these elements are below the leading diagonal, all are 0. So it is upper triangular matrix. So we can represent this in another way. It is Aij is equal to 0 when I greater than j. So this means what is the position of this, children? It is 2, comma 1. Okay, 2, 1. This actually what? 3, 1. This actually what? 3, 2. Paranga, it is 2 greater than 1, 3 greater than 1, 3 greater than 2. So it is upper triangular matrix. Okay, children, have you understood the types of matrices? Okay, thank you. Next, then equal matrices, children. Equal matrices means the matrices are with the same order, okay, and the same elements called the equal matrices. Okay, children, if I take the matrix A, order is 3 by 2, then matrix B order also should be 3 by 2 only. Then only I can see the comparison whether they will be equal or not. I can think about it. So this is nothing but A, I, J. This also nothing but this is nothing but B, I, J. So this both are equal means their elements also equal. Okay, children. So children, order must be same, and the numbers or elements also. Okay, children, order and elements must be same. That's what I said. If A equal to B with the same order means, children, their corresponding elements will be equal to each other. So, for example, if I say that X, Y, ZW is a 2 by 2 matrix, I'm just equating 2, 4, 5, 6, which means I can say that X is equal to 2, Y is equal to 4, Z is equal to 5, W is equal to 6. So these two are equal matrices. Okay, children. Now when we come to the negative, just opposite sign. Children, if I take a matrix A is nothing but 1, 2, 3, 4 mean, children, the negative of the matrix is nothing but minus A, which is minus 1, minus 2, minus 3, minus 4. That's all, children. Okay, so this means if A is equal to Aij, okay, implies minus A is nothing but minus Aij. All the elements involving in this matrix will be put, we will be having minus sign, opposite sign. That's all. Okay, children. Now, operation on matrices. Addition and subtraction of matrices. Children, the condition for addition and subtraction, they must have same order. Okay, same order. Must. Okay, children. Then we can add the corresponding elements. corresponding elements. So for example, if I take the matrix A as what? 1, 2, 3, 4, 5, 6. You know what order it is? It is 2 by 3. Okay, now I am taking the matrix B. It is 5, 6, 7, 3, 4, 1. This also 2 by 3. If it is different order means it's not possible to add. So your A plus B is nothing but 1 plus 5. Children, corresponding elements should be added. So here 1 plus 5, 6, 2 plus 6, 8, 3 plus 7, 10. Then 4 plus 3, 7, 5 plus 4, 9, 6 plus 1, 8. Okay, children, this is what. So A plus B is equal to this one. Even we can do the subtraction also, children. Similar way you can do it. Okay. Multiplication of the matrix by scalar. What is multiplication of the matrix by scalar? Scalar is nothing but a constant. Okay, nothing but a constant like a k. So you can multiply any matrix by scalar. That means ka. If I have the matrix A is equal to 1, 2, 3, 4, children, I can say that ka is nothing but k into 1, k into 2, 2k, then k into 3, 3k, k into 4, 4k. Okay, children. So like this, we can say. Okay, similar way we can say some matrix, it is 5A. So that means I can say that 5 into 1, 5, 5 into 2, 10, 5 into 3, 15, 5 into 4, 20. What does it mean, children? Multiplication of matrix by any scalar is nothing but multiply the element involving in the matrix is what? By the number whatever we use over here. Okay, children? Yeah. Then there are the properties. Okay, properties of matrix addition and scalar multiplication. Children, so this means here we can say that first one, A plus B is the sum of the two matrices. It's nothing but B plus A, children. It is commutative. Okay, commutative. Then similar way, children, you can check this example. This is a simple one. Okay, now it is associative also. A plus B plus C is nothing but A plus bracket B plus C. It is associative. Okay, it is associative. Then next, children, it is about the scalar. If I take that one scalar P and Q is multiplied with the matrix A, it can be written as PQ into A or P into QA. Children, even you can write Q into PA also. It's a number only, no? It can be multiplied like this. Okay, children. If I multiply the scalar with the matrix A and the sum of the matrix A and B, that means what will happen? PA plus PB. Okay, children. So like this, we can do. Even we can say that sum of the two numbers I'm taking, children, as the scalar P plus Q, I multiply with A is nothing but PA plus QA. Children, these are the things. Scalar, no, you can multiply however you like. It doesn't make any difference at all. Okay, children? Yeah. Now, additive identity. Children, what is additive identity? You would have heard about it. Children, any number is added with the particular special number, you will get the same number. Then what is a special number? 0, children. So if I write that A plus 0, it is A. I will be getting the same number. Okay, is equal to 0 plus A. You understand? This is what. So this happens in the matrix also, children. So here we say that 0 is nothing but 0 matrix. Okay, 0 matrix. So 0 matrix is additive identity matrix. Additive identity matrix. Okay, children. Similar way for additive inverse. Hope you remember the additive inverse. That means actually the opposite sign. Children, so additive inverse of 2 is nothing but minus 2. Same thing we are going to do with the numbers. Okay, children? That means the matrices. Sorry. Same thing we are going to do with the matrices. That means additive inverse of the matrix A is nothing but the negative of its matrix minus A. Children, you know what is the speciality? If you had the number and its additive inverse, you will get 0. No, it is additive identity. See, so similar way, children, if you add the matrix A with the its additive inverse, you'll be getting 0 matrix. You understand? That's all. These are the speciality over there. Okay, children. So additive identity is the 0 matrix. Additive inverse matrix is nothing but negative of the matrix. Okay, children. Now, matrix multiplication. Children, two matrices to be added. For that, what did we do? Order must be same. Then only we can add the corresponding element. Like that we said. That is a condition. Order must be same. Like that we can have for the multiplication also. If I consider the matrix A as M by N, the matrix B as some P by Q. I'm taking. I want AB defined, the product of A and B is defined only if, children, the column, see that M by N, when we say N represent number of column, here Q represent number of column, P represent number of row, M represent number of rows. Okay, the number of columns in the first matrix should be equal to number of rows in the second matrix. So N is equal to P. Okay, children. So what do you understand from this? Number of rows, sorry, columns. Number of columns in first matrix equal to number of rows in second matrix. Okay, children, that's what here they are telling, that they took M by N and N by P. Here, this both must be equal. See here, yes, yeah. Then only the multiplication is defined. Then if you multiply, you'll be getting the one more matrix one. What will be the order of that resulting matrix? That also we can say by seeing the order of the given two matrices itself. That's what, children. See here, the row of the first matrix, then column of the second matrix. Okay, children. So this is what. So how will you multiply? To multiply the two matrices. Here they have taken the matrix. One is 3 by 2. This is 2 by 3 matrix. See, children, here this column, the second matrix row, both are equal. So we can multiply. How to multiply? See, children, multiplied by the elements in the row of the first matrix by the elements in the column of the second matrix. See that? That's what the procedure. You take the row with the columns. Second row with the 3 columns. Third row with the 3 columns. Now see, you can see AB with the GK. So A into G, AG, B into K, BK. You have to add. See, adding the results. Then A into H, AH, B into L, BL. Then A into I, AI, B into M, BM. Like that we should add. I do one example for you, children. I take a matrix A as 1, 2, 3, 4. Okay, it is 2 by 2, I took. Then matrix B is 2, 3, 4, 1, 2, 3. Children, it is 2 by 3 matrix I took. Now I can multiply. How can I say it is multiplication is possible? See, children, the column in the first matrix, row in the second matrix, both are same. So I can multiply. So AB is nothing but, I'll be writing it is 1, 2, 3, 4. See, the next 2, 3, 4, 1, 2, 3. Okay, now see what is happening, children. Here I took the first row with the first column. So that means 1 into 2, 2, 2 into 1, 2. Okay, now I take the first row with the second column. 1 into 3, 3, 2 into 2, 4. Then first row with the third column. 1 into 4, 4, 2 into 3, 6. Okay, now I take the second row. Children, I take the second row. Second row with the first column. So that means 3 into 2, 6. 4 into 1, 4. Next, second row with the second column. It is 3 into 3, 9. 4 into 2, 8. Then second row with the third column. It is 3 into 4, 12. 4 into 3, 12. Children, I got it. Now I can add this. What will I get? 4. This 3 plus 4 is 7. 4 plus 6 is 10. 6 plus 4, 10. 9 plus 8, 17. Then 12 plus 12, 24. Children, I got, see the answer matrix order. What is it? It is 2 by 3 only. See here, this and this. Okay, we get it. Okay, children? Yeah. This of multiplication of matrices, children. Properties. Here, children, in this, we can say that it is not commutative. Matrix multiplication is not commutative. Children, AB is not equal to BA. That's what they're telling. We have seen before, matrix addition is commutative. Yes, of course, it's just addition. But here, why it is not? The first simple idea, we can say A is 3 by 2. B is 2 by 4 I took. Okay, ma? So here AB is possible. AB is possible. You know why? Here these two are equal. Okay, children? Yes, two columns, here two rows, AB is defined. But what about BA? When we check BA, what is B? B order is 2 by 4. A order is 3 by 2. Children, here you can find the column in the first matrix, row in the second matrix not equal. So BA is not defined. You understand? BA is not defined. This is what, children. So AB not equal to BA by using this rule. Children, we may be thinking, sir, order same. Appo what will happen? Yeah, I'll say the second one also. Okay, so here A is 2 by 2, B also 2 by 2 I'm taking. So that means I take the matrix A as 1, 2, 3, 4. The matrix B is 2, 3, 1, 4, 1. Like this I took. I find AB because it is defined 2 by 2, 2 by 2. So what will I get? It is 1, 2, 3, 4. Then it is 3, 1, 4, 1. I multiply, children. You know, just now we studied the multiplication. 1 into 3, 3, 2 into 4, 8. 1 into 1, 1, 2 into 1, 2. Then 3 into 3, 9, 4 into 4, 16. 3 into 1, 3, 4 into 1, 4. Okay, children, I got this one. So the answer I'm getting, you know what it is? 11, 3, 25, 7. Okay, now I find for BA. Okay, it is 3, 1, 4, 1. It is 1, 2, 3, 4. You multiply these two, children. 3 into 1, 3. 1 into 3 also 3. Now 3 into 2, 6. 1 into 4, 4. Now for second row, 4 into 1, 4. 1 into 3, 3. 4 into 2, 8. Plus 1 into 4, 4. Children, see what we are getting. It is 6, 10, 7, 12. See, are they same? So from this we can say AB not equal to BA. Okay, AB not equal to BA. Do you understand? Matrix multiplication is not commutative even though BA defined. Here BA defined. Okay, children. In this case, AB and BA defined, but not equal. So matrix multiplication is not commutative. Children, matrix multiplication will be commutative for some cases that I'll be telling in the next. Okay. Yes. Matrix multiplication is distributive over matrix addition. Children, this and all simple children. Directly, if I write itself, you can understand. A into B plus C. Children, these are the matrices A, B, C. They are satisfying the condition for addition and multiplication. Okay. Now it can be written as A into B plus A into C. It can be done, children. Okay. Yeah. The next, it is associative. They are telling matrix multiplication is associative, always associative. See, children, it is A into B into C is nothing but A into B into C. Is it clear? So this is how. This is actually true for all the cases. You can substitute and check. Then matrix multiplication by unit matrix, children. What is unit matrix? We have studied unit matrix. That means all the leading diagonal elements are equal to 1. Okay. So I took that 1, 0, 0, 1, 2 by 2 matrix. I take any other matrix. It is I. Okay, I take any other matrix. It is 2, 3, 4, 5. See what's happening here. Children, 1 into 2, 2, 0 into 4, 0 only. I'm not writing. 1 into 3, 3, 0 into 5, 0 only. 0 into 2, 0, 1 into 4, 4. Then 0 into 3, 3, 0, sorry, 1 into 5, 5. And see, children, what I'm getting? When I multiply I into A, I am getting A itself. Similar way, children, if you multiply A into I, also you'll be getting A only. So here it is commutative, children. AI equal to IA is equal to A. You can check that. It is commutative. So if it is what? Multiplicative identity involves. Okay, children. So here the identity matrix. Okay, identity matrix acting as what? A multiplicative identity. It is multiplicative identity. Okay, children? Yeah. Now, children, we will have one confusion, no? In a, sir, if x and y, when you multiply 0, na, okay, either x0 or y0, like that we will say, sir. Then what about for matrix? If A be 0, is it necessary to A equal to 0 or B equal to 0? Children, it's not necessary, they are telling. It is not necessary. So I took the example over here. Okay. So now when I multiply these two, I'll be getting 0, but this matrix A non-zero, matrix B is also non-zero. Now see how it works. I just check A, B. That means I write this numbers 1, minus 1, minus 1, 0. B is 1, 1, 1, 1. Okay. So now see what is happening. I multiply 1 into 1, 1. Minus 1 into 1, minus 1. Okay. Yeah. 1 minute, children. I just 1. I took wrong. Okay. Yeah. So now next 1 into 1, then minus 1 into 1, minus 1. Then minus 1 into 1, minus 1, 1 into 1 plus 1. Minus 1 into 1 minus 1, 1 into 1 plus 1. See, children, what I'm getting? It is what? 0, 0. This also 0, this also 0. See, my product of A and B is 0. But A is non-zero, B is also non-zero. See, children, this happens in matrix, but not in the numbers, real numbers. Okay, children, you try to understand. That's why we gave this as a note. Now, next, children, here A and B are two non-zero matrices we took. Children, we know that AB is not equal to BA. We know this one. AB is not equal to BA. So that means you just think about this. A plus B whole square, we will be writing A plus B into A plus B. So what will happen? A square plus AB plus BA plus B square only. Children, AB not equal to BA, pa, then how can we say that it is 2AB? AB is not equal to BA? No, that is why here we mentioned that they are not equal. But if AB is equal to BA, it is possible. Okay. Yes, if AB is equal to BA, we can say that A plus B whole square is equal to A square plus 2AB plus B square, but not for all the cases. If AB not equal to BA, na, it is not at all possible. Okay, Chitra. Now, operation of the transpose of matrix. What is the operation of transpose? Transpose, we know that it is matrix A is there means its transpose is A dash. Children, so how it works? We know that one. But here the properties you can see A dash whole dash. Children, I take the matrix A as what? 1, 2, 3, 4, 5, 6. You know what order I have taken? It is 3 by 2. Then what is its A transpose? Children, the column will become row, row will become column. That means interchange of the rows and columns. So 1, 2, 3, 4, 5, 6. Now see what is happening. It is 2 by 3 children. Now A dash whole dash I am finding. For this I do the transpose. Now again what will I write? 1, 2, 3, 4, 5, 6. See, I am getting the order 3 by 2 same matrix. That's what here they are telling. So then this and all actually what if you multiply by the scalar, you will be getting the same only. It doesn't matter. So then you can add or subtract also sum of the two matrices and taking the transpose, you'll be getting the what? Taking the transpose of the two different matrices and adding, that will be equal to A plus B whole transpose. Okay, children, this and all you can do on your own. It's not very difficult. Now see this one, children, AB whole dash equal to B dash and A dash. Children, please verify this with the example. Really it will be possible. Okay, so that means what is the property? AB whole dash is equal to B dash into A dash. Children, please don't write AB whole dash is equal to A dash B dash. It is wrong. Okay, AB whole dash is nothing but B dash into A dash only. Okay, children? Yeah. Now, symmetric matrices. Symmetric matrix. Children, if you transpose the any matrix A, okay, if you transpose any matrix, if it is equal to the given matrix itself, we can say A is symmetric. A is symmetric. You understand? So now I just give one example for this. If a matrix A is, I just write 1, 2, okay, 2, 3. See children, 1, 2, 2, 3. What is A dash? Children, this itself same only 1, 2, 2, 3 only I write. It is nothing but A. We can say it is symmetric. You can give for 3 by 3 matrix also, children. Okay, so a simple thing you should suppose know, if the transpose of any matrix is itself, okay, transpose of any matrix is the given matrix itself, means the matrix is called symmetric. Now we come to the skew symmetric. The transpose of the given matrix is negative of the given matrix. Negative of the given matrix means we can say it is a skew symmetric matrix. See that we can say the example, children, A is equal to 0, minus 1, 1, 1, 0, 3, minus 1, minus 3, 0. I took this matrix. Children, find the A dash transpose 0. The row become column 1. Then 1, 0, 3. Third row become column minus 1, minus 3, 0. Children, just take the minus out. Now see what is happening. 0, minus 1, 1, 1, 0, minus 3. Okay, children, then it is minus 1, minus 3 and a 0. Children, I am getting what? Same A itself. Same A itself. Is that clear? That's all, children. So therefore, matrix A dash, no, you are getting A, but negative of A. Yes or no? Negative of A. Therefore, we can say that A is what? Skew symmetric matrix. Children, here we can say one more thing. A, I, J. Transpose is nothing but same Aij itself. Okay, so here you know what is happening. Aij is nothing but negative of A ij itself. Okay, transpose. Yes, so this means from this, when I equal to j, what will happen? Then aii equal to minus aii is nothing but 2aii. It is a equal to 0. So this implies aii is equal to 0, children. Aii equal to 0. What does it mean? All the leading diagonal elements are 0. Okay, children, in Q symmetric matrix, we can observe all the leading diagonal elements are 0. Okay, you can see the theorem 1. For any square matrix A with real number entries, okay, A plus A dash is symmetric, they are telling. A minus A dash is Q symmetric. We prove that one. Let us consider C equal to A plus A dash. I just put A C dash. That means A plus A dash whole dash. Children, we have seen in the property of the transpose of the matrix A plus B whole dash. A plus B whole dash is nothing but A dash plus B dash. In that way, we can write it is A dash plus A dash whole dash. So what will happen? It is A dash plus A. See that I am getting same C itself. So therefore, I can say that A plus A dash is always symmetric. What does it mean? If you add the matrix and its transpose, the resulting matrix will be always symmetric only. Okay, now next. Then we take B equal to A minus A dash. Then now I am finding B dash. It is A minus A dash whole dash. Children, what will I get? A dash minus A dash whole dash. What does it mean? It is A dash minus A. Children, I take minus out. That means minus A dash plus A is nothing but minus of A minus A dash. I am getting same B minus B. So we can say that A minus A dash is always Q symmetric matrix. Okay, children? Yeah. So what does it mean? Difference of a matrix and its transpose will give you the Q symmetric matrix itself. Okay, children? Yeah. Now here see the next theorem. Any square matrix can be expressed as the sum of the symmetric and the skew symmetric. Sum of the symmetric and the skew symmetric. See, children, we know what is the symmetric and what is the skew symmetric. See, children, we know that A plus A dash is symmetric. A minus A dash is skew symmetric. Children, this implies half of A plus A dash is also symmetric. Okay, then this implies half of A minus A dash is also skew. You agree with me? Because just to multiply by number, the symmetric, symmetric and the skew symmetric idea will never change. Just add them. Half of A plus A dash plus half of A minus A dash. Children, what will you get? Half of, then half common, no. I'll write A plus A dash plus A minus A dash divided by 2. This A dash will get cancelled. 2A by 2. Children, I am getting A itself. So what does it mean? I can represent any matrix, square matrix A as the sum of symmetric plus Q symmetric is nothing but given matrix. Okay, children. So this is what the theorem 2 says. Children, definition of the inverse of a matrix, of a square matrix. Children, do you remember 2 into 1 by 2? What it is? 1. And we will say 2 plus minus 2 is equal to 0. We studied in small classes. Now, what will you say about this 1 by 2? What will you say about this minus 2? Children, this 1 by 2 is multiplicative inverse of 2. This minus 2 is additive inverse of a 2. Correct? Yes, like that we can have in the matrix also. Yes, children. So, what I'm going to do now? I'm going to take a matrix A. I'm going to multiply with B. See, children, what did I get? Multiplicative identity 1. When I multiply a number and its multiplicative inverse, I got the number 1, that is multiplicative identity. When I add the number and its additive inverse, what I'm getting? I'm getting the additive identity. Similar way, children, when I multiply two matrices, okay, if I get the identity matrix, okay, even I can write BA also. This happens means, okay, if this product of two matrices giving you what a identity matrix means, we can say that B is the inverse. One of the matrix is inverse of the other. Inverse of A. Okay. Or A is the inverse of B. Children, this means B is equal to A inverse. We will represent the inverse of the matrix as a inverse. Children, A inverse is inverse of A only, not 1 by A. Be very careful. Okay, just the representation. Okay, this implies here A equal to B inverse. Children, it is not 1 by B. Please do remember this always. A inverse means not 1 by A. A inverse is just a inverse of A only. Okay, children, so try to understand this. Okay, in the multiplication of the numbers and all, we can say it is. Okay, here minus 2 we are telling, here 1 by 2 we are telling. It is for the number, but for the matrix, we represent only what a inverse symbol, that is in power minus 1, but it is not equal to 1 by A. Okay, children? Yeah. Now, see the theorem 3. The square matrix has inverse, then it is unique. It is unique. Okay, children, I just take a matrix A. It has two inverses. I consider, I just like inverse. Okay, so like a B and a C. I consider. Children, that means what will I write? AB equal to BA equal to I. I should suppose write this. AB equal to BA is equal to I. Correct? Huh? Then from the second one, I will write what? AC equal to CA is equal to I. Okay, wa? Yes. Now, see children, I am going to write this B is equal to, I am writing as what? BI, because any matrix is multiplied with identity, I'll get the same matrix. That is why I write. Now, you know what I'm going to write? I'm going to write instead of I, AC. Instead of I, I'm going to write what? AC. Okay, children. So this implies now it is BA into C. Associative property. I'm writing. You know, children, what is BA? BA is I into C. Children, we know what is IC? C only. So this implies we get B is equal to C. You understand? B is equal to what? C. That means what? It has unique inverse. If even though you take many inverse for the given matrix A, but all are same only. Okay, all are same only. So try to understand this one. Okay, children. Now, next, right cancellation law. Children, there are three matrices we are having A, B, C. These are all square matrices only of order n. Okay, same order because square matrix no. And children, this BA equal to CA means B equal to C we have to prove. I'll just take BA equal to CA. I need to prove that B equal to C. Children, I am going to multiply by A inverse on the right side. That means a post multiplication A inverse. Here CA into A inverse. Okay, children. Now see, it's associative property, no? In that B into A inverse I am writing. Then here C into A inverse I am writing. Children, just now we learned A into A inverse. That means what? A, B equal to I, BA equal to I. We said no. That means A, B is the inverse of A. A is the inverse of B. We said no. This implies we can say that A into A inverse, then A inverse into A is equal to I. Okay, children. So with that way, we can say this is I. Then C, this is also I. Children, this is nothing but B is equal to C. We proved. Okay. Yeah. Next, reversal law for the inverse. A and B are two matrices of the same order. Okay. The product AB is also okay. The non-singular and all we'll be learning in this determinant. Okay. AB whole inverse equal to B inverse into A inverse we have to prove. Okay. Children, what is AB whole inverse? Is inverse of AB. Okay, ma? Here we can consider this both are equal. No, I consider let B inverse into A inverse is inverse of AB. Okay, so if I prove that, it is enough. So what I'm going to do, children, so this means I'll write AB into B inverse into A inverse. If I prove this is equal to I proved this one. Okay, now see children, I'm going to take AB into this B inverse with the A inverse over here. You know that B into B inverse is I. Okay, into A inverse. Children, we know that A into I is what? A. Then A inverse. Children, A into A inverse is nothing but I. I got it, children. Okay, now see the reverse process also. B inverse into A inverse into AB. Now see, I do this B inverse bracket, A inverse into A into B is equal to, children, B inverse into, this is I, A inverse into A is I, then B. Children, B inverse into I is nothing but B inverse only into B is nothing but I. am getting, children, I proved that B inverse into A inverse is the inverse of AB. This implies AB whole inverse is nothing but B inverse into A inverse. Okay, children. So this is how we need to prove the what AB whole inverse equal to B inverse A inverse. This is called a reversal law for inverses. Now, theorem 6. Law of double inverse. That means A inverse whole inverse is equal to A. Children, we know that A inverse into A is equal to A into A inverse is equal to I. We know this one. Okay, children? Yeah. So now what I'm going to do, I just going to let this A into A inverse is equal to I. I'm going to take the inverse on both sides. That means what? A into A inverse whole inverse is equal to I inverse. Children, I inverse nothing but I itself. Okay, now we have studied the rule the previous before. AB whole inverse is nothing but B inverse into A inverse. So which means what will I write? A inverse whole inverse into A inverse is equal to I itself. Now I'm going to post multiply by A. Post multiply by A. Okay, children, that means A inverse whole inverse into A inverse into A. Then I into A. What did I do? Post multiply by A. Okay, children? Yeah. So this means what will I get? This A into A inverse become I. Therefore, A inverse whole inverse is nothing but I into A itself. Okay, children? This is how we prove the what? Law of double inverse. Okay, children? Now, children, right cancellation, we did know left cancellation. That means there are three matrices we are having A, B, C. Children, here they are telling that AB is equal to AC. AB is equal to AC. This means we have to prove that B equal to C. Left cancellation. Children, what I am going to do? I am going to pre-multiply by A inverse on both sides. That means what will happen? A inverse A into B, then A inverse into AC. Okay, children? Yeah. So now by the associative law, you can say that A inverse A into B, then A inverse A into C. Now A inverse A is I, then B. This A inverse into A, that also I into C is nothing but I into B is B, then I into C is C. Okay, children. So this is how we finish the matrix. Okay, children. Hope you all understood. Any doubt you can ask through WhatsApp. Okay. Thank you, children.